Today we'll take some points on this particular topic called carbohydrates, which comes under a part of the biomolecules. Some examples of these carbohydrates like glucose and glyceraldehyde. If you observe their formulas, molecular formula of the glucose is C6H12O6. Glyceraldehyde has a formula C3H6O3, which can be summed up like this: CnH2ON, which gives a misleading idea that all the carbons in this compound are attached through the H2O molecules. So therefore they named as a carbohydrate. Hydrate means water attached molecules. So they thought initially all these molecules will have the carbons and attachment with the H2O, which is proved later wrong and redefined as the definition of the carbohydrates. Modern definition is they are polyhydroxy optically active carbonyl compounds. So there are 3 points we are defining. Polyhydroxy means a number of OH groups should be there, n number of OHs. Optically active means the lowest the understanding of this level understanding is a carbon containing the 4 different groups. Such a carbon we identify as a chiral carbon. If A, B, C, D groups are there, such a carbon we can call it as a chiral carbon. That optical activity comes around about this particular presence of this carbon. A carbonyl compound means it can be a aldehyde function or ketone. Aldehydes means one side hydrogen you can have. You can also alkyl or a hydrogen or any aromatic group. Or it can be a ketone. Ketone will not have a hydrogen, either alkyl or aromatic, or alkyl or aromatic. These are the ketones. So obviously here there is no aromatic system, so all aliphatic carbonyl compounds are there. So one such example is the lowest possible compound is an aldehyde containing the second carbon OH and third carbon also OH. The remaining will be fulfilled with the hydrogens. So there is one chiral carbon. Polyhydroxy has come now here. 2 OHs. 2 OHs, minimum is 2 OHs. Actually 2 cannot be poly, but still as a limitation we have here 2 is taken as a lowest for the polyhydroxy type, and there is an aldehyde function. With this formula you have another compound also like this. A carbonyl compound is there and 2 hydroxy is also there, but here we are missing the chiral carbon. So therefore as per the definition this won't be the carbohydrate. It is nothing but the 1,3-dihydroxypropanone, which is no more a carbohydrate. But this is a 2,3-dihydroxypropanaldehyde is called glyceraldehyde, as we have seen already. So let us have different examples and taking the classification of the carbohydrates. In the carbohydrates classification is one of the important topic. Let us see the classification of the carbohydrates. The modern classification shows they are classified based on hydrolysis. The compound which on hydrolysis will not give any further breakages or hydrolyzes into pieces is called monosaccharide. That is the carbohydrates, also called sometimes referred as saccharides or saccharides. These are first base is called monosaccharides. Monosaccharide means which on hydrolysis with acidic catalyzed hydrolysis, no more further hydrolysis. No further means this is the smallest saccharide. If you can hydrolyze into two pieces, they are called disaccharides. Disaccharides means on hydrolysis you are getting the two monosaccharides. Two monosaccharides. Similarly, you can also go for the trisaccharides and tetrasaccharides and so on. But in some books are giving, we are getting another section called oligosaccharides. Oligosaccharides means on hydrolysis you are getting 3 to up to 10 monosaccharides. When you are getting that type of these saccharides are called oligosaccharides. On hydrolysis, if many you are getting, that is called polysaccharides. Polysaccharides. Polysaccharides means huge number of, that means at least minimum more than 10 and number of monosaccharides if they are coming. Such a saccharide is called polysaccharide. So, monosaccharide means no further hydrolysis, no further hydrolysis. So, for example, under this class we have glucose, fructose, ribose and so on. These are the main examples. Under disaccharides we have cellobiose, maltose, sucrose, raffinose is an example for the oligosaccharide. Polysaccharides we have starch is a best example, and cellulose is also one of the polysaccharide. The examples based on the examples we are getting the question. So, you may collect some more examples for each variety and you can go through it. The monosaccharides are further classified. They are further classified based on the number of carbons. How many carbons are there? Based on that, the classification goes like into trioses, tetroses, pentoses and hexoses. That is how many carbons are there. Based on that, triose. Triose is a glyceraldehyde example. Glyceraldehyde is the tetrose, erythrose and triose. Erythrose and triose is the examples for the tetroses. For pentoses, ribose, which is a constituent of the DNA and the RNA. RNA contains polyribonucleic acid is the DNA RNA. And second carbon, if OH is missing, it is called 2-deoxyribonucleic acid is the DNA. Both contain this 5-membered ring, pentose. Under the hexose, we have seen glucose and the fructose. Glucose and fructose are the examples for these. Again, this hexoses can be classified into the two varieties based on the functional group. What type of functional group we have? Aldoses and the ketoses. Aldoses and ketoses. In fact, glucose is an example for the aldose and the ketoses, fructose is the example. Like that, each member, pentoses, triose, tetrose also can be classified. So, glucose is an aldose, glucose is a hexose, glucose is also a monosaccharide. Glucose ultimately is a carbohydrate or it is a saccharide. But because it is not further hydrolyzed, we said it is monosaccharide. Because it contains 6 carbons, we said it is a hexose. And the glucose contains a aldehyde function, therefore it is called aldose. So, based on this, the first based on the hydrolysis concept. Second one, second step is in fact based on the number of carbon atoms in the carbohydrate. The third point we have taken here, what type of carbonyl function is there? Is it aldehyde or a ketone? Based on that we have taken into this type, isn't it? Some books also gives the carbohydrates into which reacts with Tollens reaction and which are not able to give. Based on that reducible sugars and non-reducible also you can classify. In fact, both aldehydes, specifically glucose and fructose, both are coming under the reducible type of the glucoses. So let us take some specific points related to the glucose. So it's a structure determination. If you take it, some important points which are related to the structure, we can notice point by point. One is its molecular formula is C6H12O6. That means there are 6 oxygens are there and 6 carbons are there, remaining are the hydrogens are there. This is what the exact number of the carbons we have in this compound it is showing. It's the glucose on reduction with HI and phosphorus. It's a strong reducing agent. All oxygen functions like hydroxy, carbonyl functions and acids, acid derivatives and alcohol derivatives will be converted. Acid derivatives also will be converted into their hydrocarbon. So here you got a N-hexane. That means 6 carbons are there, all are hydrogens only, there is no other the oxygen. That is, all oxygens contained in the glucose, 6 oxygens were there, all were reduced to give their corresponding product. So this the reaction shows all the 6 carbons are in straight chain. The chain is in the form of a straight chain. There is no branch, specifically branches are not there. If a branch is there, we too could have get a branched hexane. So formation of a straight N-hexane formation shows clearly that there is no branch present in the glucose. Glucose reacts with the HCN, forms a cyanohydrin. This clearly indicates that there is a carbonyl function is there, which is can be an aldehyde or it can be ketone, because cyanohydrin formation observed in the both the cases. So at this stage we cannot say it is aldehyde or a ketone, but the glucose after getting the cyanohydrin is hydrolyzed. You will get a carboxylic acid. A carboxylic acid is formed. This acid on reaction with HI and phosphorus, you will get a N-heptane. That is previously on reduction N-hexane. Here now you are getting N-heptane, 7 carbons. That is, 1 carbon is added through the cyanide, and this carbon previously we got already N-hexane, and 1 carbon is added where and the one of the end. So the last carbon must be the added carbon in the form of cyanide. So where that cyanide is added means on the one of the end of the glucose. That shows the carbonyl function must be on the one of the end. That also confirmed by the glucose reacts with the bromine water. It is a mild oxidizing reagent, gives a carboxylic acid known as gluconic acid. This is without any disturbing the number of carbons. Its gluconic acid is on reduction also gives an hexane, shows 6 carbons are there. Oxidation gives means it must be an aldehyde. Glucose also gives tests like Tollens test, failing test. All these tests positive reactions are coming. That shows there is an aldehyde function is there. So the cyanide reaction also proves that the carbonyl carbon is on the last carbon, therefore there is an aldehyde is there. Lastly, we can also go for one more point. The glucose when treated with the acetic anhydride, all the OHs in this reaction will become into OCOCH3. That is, acetylation takes place in this reaction. The hydroxy groups are converted to acetylation. So the glucose gives a pentaacetyl derivative. pentaacetyl derivative. This pentaacetyl derivative is confirmed by how many acetic anhydrides are used, or you take 1 mole of pentaacetyl and hydrolyze it. Each mole gives 5 acetic acid. That also confirms there are 5 OHs are acetylated. That means the presence of the 5 hydroxy groups are there. Now, after observing all this, the 3-4 points, we can come to a conclusion that so the first point shows the 6 carbons which are in the straight chain, second point, and the one of the end is carbonyl function, that is aldehyde, remaining oxygens are hydroxy. So, a tentative structure may be proposed that the 6 carbons having the aldehyde function on the one end, remaining OHs as per the organic chemistry rule, general rule, you cannot have a 2, 2, 3, 3 OHs on each carbon. So, 5 OHs, 5 carbons, it is the problem is resolved. So, remaining you can take it as a hydrogens. So, this is the tentative structure of the glucose, and we have therefore the 1, 2, 3, 4. 4 chiral carbons are there. So, therefore, 2 to the power of 4 means 16 the optically active compounds you get it. Out of that, 8 will be the optically positive, that is dextro, and the 8 will be the levo, and the symmetry at second, third, fourth, fifth is slightly difficult to this one, but Emil Fischer guessed and he has given one structure without going to the chemically, that is much proofs and all that. So, second carbon OH is at right side, third carbon OH left side, fourth one right side, fifth one right side, the sixth one is a non-chiral carbon, first one is also non-chiral. You can write carbonyl group this side, hydrogen that side also, but the rest of the HOHs should be very clearly, specifically the third OH you write it on the left side, remaining other 3 OHs on the right side. This is the absolute configuration of the glucose. So, with this the 50% of the structure of the glucose is established through these 4-5 points. Now, let us go to the second part of the structure of the glucose, that is called a cyclic structure of the or ring structure of the glucose. Already we have established nicely the structure. What is the necessity to go for this cyclic structure means glucose is showing some mysterious or the properties which cannot be easily explainable. Such a properties it is showing. The glucose is not reacting the Schiff reagent. Schiff reagent, when you add, generally whenever there is an aldehyde function, the Schiff reactions will get, but it is not showing, means a negative reaction it is showing. That shows whether this aldehyde function is really there or not. Already we established, but now we are getting a doubt. If the aldehyde is there, it should give immediately pink coloration. So, it is not giving, means we get a doubt. This is the point number 1. Second point, glucose shows some specific observation. When the glucose freshly prepared solution you take and convert into a hot saturated solution, this you can convert into the crystals in 2 different ways. One is go on boil it. At hot condition, crystals are formed. They are identified, named as alpha glucose crystals. The other one is instead of go on boiling, you just cool it, then also you will get crystals of the another glucose called beta glucose. And these 2 compounds are having the difference in the boiling point, melting point, and they are showing optical activity also. Different optical activities are there. One shows approximately around 19 degrees optical activity, plus 19. The other one shows around 112 optical activity. That is, these 2 are crystals. Crystals, solids will not be directly showing the optical activity. You have to dissolve in a suitable solvent or in the form of the liquid, you can check. So, take the crystals, freshly prepared glucose, dissolve in a water, and fresh solution you take it and then observe the optical activity, you will get 90. But what happens is, as the time passes on, as the time passes on, the value is going on increasing, and then it comes to a 52.7 plus 52.7 degrees, and there it will stop. Similarly, this as the time passes on, the value goes on decrease now here and comes to 52.7, and then it will stop there. Why these freshly prepared solutions are having slight difference in the value, and after some time why it is increasing and decreasing, coming to a some value, and there it is stopping. This observation is specifically said as a mutarotation. The whole phenomena we are calling as a mut, means changing, mutarotation, changing rotation. So this mutarotation is not that easily explained by the open chain structure. Another one is generally all the carbonyl compounds react with 1 mole of alcohol and gives the hemiacetal. Another mole of alcohol gives the acetal. But the glucose, we already said it is a aldehyde is there, but this glucose reacting with only 1 mole of glucose, 1 mole of alcohol, methanol or ethanol you take, and it is giving directly acetal. Not the 2 moles, only with 1 mole it is giving acetal. How the glucose gives this type of the reaction means we get a doubt, is the glucose is a carbonyl compound or hemiacetal. Is this glucose is a hemiacetal? The question is it aldehyde function or hemiacetal? Means if it is aldehyde, it is not explaining this property. So it may be hemiacetal. To get hemiacetal, we need carbonyl compounds and the hydroxy, where from the hydroxy means already in the structure we have seen there are a number of OHs are there. So therefore answer is one of this OH, initially the 4th one we had, but finally it is proved that the 5th one is a hydroxy group is reacting with this one, and this O will become into OH. That is, the OH is added on the carbonyl group, showing a nucleophilic addition. A cyclic structure is established, 2nd OH, 3rd OH, 4th OH. 5th OH is added to the carbonyl, and we have a last one is a non-chiral, that is CH2OH. So this is a partly we explained that because the glucose without adding the methanol, it gives the hemiacetal, and while forming the hemiacetal, the OH can be right side or it can be left side also. That's why 2 different types of the glucose molecules are forming with reference to the symmetry at the first carbon. So 2nd and 3rd and 4th will be same, but at first carbon we have a chance of getting the right side OH, left side OH. Right side OH we designated as a alpha gluco. This is a 5-membered carbon with 1 oxygen is called pyron ring, therefore it is called pyranoside. Pyranoside. This left side one is called beta glucopyranoside. Beta glucopyranoside. So both these 2 glucoses exist in equilibrium through the open chain. Directly they will not. It becomes into open chain. Open chain will become into beta, beta will become into open, open will become into this. So open chain will be in between these 2 structures, and these 2, that's why they are existing 2 different values are showing optical activity. While you prepare fresh one, it shows 19 and 112, but when you put into the water, it becomes into open, open becomes into this one, all mixture is coming. So this plus 52.7 is nothing but the optical activity of the mixture. In this mixture, it is proved that beta glucose consists around 64%, and this contains 36%. Literally the open chain will have almost 0, but it is very closer to the 0.02%. That is almost 0% open chain structure will be there. More will be the only the ring form will be there, out of which beta glucose will have the maximum structure. So that's why the glucose as such it itself is a hemiacetal because of the reaction internally with the hydroxy with this carbonyl. This hemiacetal, when you add 1 mole of methanol, only just 1 mole of methanol, this OH will become into OCH3. Acetal will have a 2 ethers, COC ether, and this is also a ether with the 5th carbon attachment is ether. So 2 ethers on the same carbon is called what? Acetal. So therefore this type of the methoxy and the COC function formation requires only 1 mole of methanol is also beautifully explained by this open chain structure. Next we will take the how to write this cyclic form, specifically in the Haworth form, and from the open chain structure how the cyclic form is forming we will write here. So, open chain structure we are sure that it will contain the straight chain containing the 4 OHs, specifically third OH on the left side, all other OHs on the right side. So, this is the open chain structure. When you write this molecule horizontally, let us hold back the positions of the OHs. The aldehyde group you can write either side, but the OHs, first OH is down, isn't it? Second OH, third OH is up, fourth OH down, fifth OH down, sixth one is CH2OH. Okay. Now, this partly I convert into the form like this. This is the first carbon, second carbon OH down, third carbon OH up, fifth carbon OH will be down, 1, 2, 3, fourth carbon OH down. Fifth carbon also will have the OH down, but it will have the CH2OH. Only third OH is up, rest are the down. Now, here there is an aldehyde function is there. This is reacting with this fifth carbon OH, not the sixth carbon OH. Therefore, in order to get the cyclic form, you just rotate this CC bond, so that the bond is rotated, you get the hydrogen will come here down, the OH will be going here, and the CH2OH will be going up. All these three will exchange, right? So, CH2OH will go to the top. Now, this OH is reacting with this the aldehyde group. It's a planar, trigonal planar, cutting here, adding can be either from this side or from that side. So, therefore, leading to give the two different the conformers in fact. So, now we get two different types of the cyclic structures, in which here you have a oxygen, first, second, third, fourth, fifth one is CH2OH, that is sixth carbon. So, if the OH is down, we call alpha. If the first OH is going to the up, we call beta, alpha, beta, okay, right. So, the OH is up means beta it is. The rest of the OHs will be as it is, second down, third up, fourth down, fifth is shifted to here, sixth carbon is CH2OH. These structures are called what? Alpha beta, alpha glucopyranoside, beta glucopyranoside. If you transfer this beta glucose into the form where the conformational model, if you write, you have a oxygen here at the fifth position. Here we have a one axial, one equatorial, axial, equatorial, axial, equatorial, axial, equatorial, axial and the equatorial. Now, see the structure of the beta glucose carefully. If you observe, at the second carbon, first carbon you have a OH which is equatorial, right? Second carbon, that is second carbon OH down, which is a equatorial. First one also equatorial. Third one OH up, which is also a equatorial. Fifth one is OH which is a down, okay, that is fourth one which is also equatorial. Fifth one we have a OH turned, so at fifth carbon we have a CH2OH which is up, which is also equatorial. All these big groups are in the equatorial, and the smaller groups, so called that hydrogens, are in the axial positions. We have studied from that is conformational analysis of cyclohexane. The hydrogens which are in axial will give the more problem to the ring, and the equatorial positions are more stabilization. So, if this OH is at equatorial, more stable. If this OH is at axial, naturally if this OH will be here at the alpha. So, this is the beta glucose. Why the beta is more stable? The question, out of the alpha beta forms, which is more stable? Beta is more stable. Why it is more stable means Rest of the groups are same, but at the first carbon, specifically at the C1 carbon, if the OH is equatorial, that gives the more stability. If the OH is axial, slight difference in the stability. So beta is more stable. That's why in the ratio also 64% beta and 36% alpha is there. So out of these two also beta will be more stable. This type of formulas are called Haworth models. This is called conformational model of the cyclohexane. So we can prove that the beta glucose existing in this particular model, all the bigger groups occupying, so that there is a less problem for this one and more stability for the system. So therefore universally the glucose is dominating in the biological products, and that too specifically beta glucose, specifically cellulose and starch existing in a huge quantity. In the sucrose also glucose will be there 50%. So the glucose stability attributes for this carbohydrates formation. Now let us take some points on the disaccharides, specifically examples for the disaccharides. Starch is a polysaccharide. Starch and hydrolysis, partial hydrolysis, you will get the maltose. Maltose is a disaccharide, which on further hydrolysis will get the 2 moles of glucose. So the question may be asked, what are the monomers present in the maltose? Maltose contains 2 moles of the glucose. Similarly, the cellulose. Cellulose is a polymer, starch is a polymer. On partial hydrolysis, you will get cellobiose. The cellobiose on further hydrolysis, again you will get the 2 glucose units. So cellobiose is constituted by the 2 glucose units. Then sucrose, this is what we use every day as a sugar, common sugar. The sucrose on hydrolysis will get the 1 glucose plus 1 fructose. And lactose, which is there in the milk, the lactose on hydrolysis gives 1 galactose and 1 glucose. So a few examples for the disaccharides, because in 1 year it is asked, the sucrose on hydrolysis gives A and B. What are this A and B? That was the small question. So remember some of the disaccharides and polysaccharides and which the components are involved in this type of the saccharides, you try to remember. Let us take some points on the fructose. Fructose is a functional isomer of the glucose, which also will contain the C6H12O6. Molecular formula is same, but the properties are different, means they are isomers. Specifically, functional group is different. The fructose is said to be which contains a carbonyl group at the second. So glucose will have the carbonyl group at the first carbon, and so let us write fructose only. Fructose will have a carbonyl function at the second carbon, and first carbon we have a hydroxy function, which is a non-chiral one, and third one OH on the left and right. Again on the right, the last one is chiral, non-chiral carbon. So 3 chiral carbons are there. It's like third, fourth, fifth, 3 chiral carbons are there. So with this structure, you are getting 2 to the power of 3 means 8 compounds exist for optically dextro compound for levo. Only 3 chiral carbons are existing. So this is the structure of the fructose, and some points related to this one is fructose also on reduction with HI and phosphorus will give the same N-hexane will come. Fructose also reacts with HCN, forming a cyanohydrin, which confirms there is a carbonyl function. But the carbonyl function is at the second carbon. We can prove that not through the tolerance and failing, because unfortunately fructose also gives these 2 reactions. Therefore, the cyanohydrin, you hydrolyze it, you will get a carboxylic acid. this carboxylic acid is treated with HI and the phosphorus. You will get a N-hexane containing a methyl group on the second carbon. This is called what? Isoheptane or 2-methylhexane. This clearly shows that the methyl group getting only on the second carbon shows that the carboxylic acid was introduced at the second, which was there by the introduction of the cyanide group. The cyanide is introduced at the second carbon. Why? Means the carbonyl group is at the second carbon, therefore 2-methylhexane is formed. Therefore carbonyl group is at the second. Second means it is obviously a ketone, right? So it is a keto compound containing the 5-hydroxy pentahydroxy 2-hexanone is the fructose. The chirality regarding at the second and third and fourth and fifth was proved by the one glucose reaction called osazone formation. If we start with glucose, glucose has 6 carbons and the first carbon is aldehyde, second one OH right side, third left side, fourth right side, fifth left side, the last one is CH2OH. This compound when treated with phenylhydrazine, NH2 is called hydrazine, a phenyl is there, therefore phenylhydrazine. The carbonyl groups undergo a condensation reaction with the hydrazine and gives the corresponding hydrogens. A double bond N-NH phenyl group containing derivatives are formed. The rest of the structure will be intact. But what happens here? Let us take this the rest party as a R1. Okay. Then the second carbon will have a OH right side, third left, fourth right, fifth right. This is a CH2OH. However, now this let us take as a R1 and proceed the reaction. It consumes one more phenylhydrazine, and from here one hydrogen, from here one hydrogen is removed, and that are added here, so that these compounds will become into one into the aniline, one will become into the ammonia. So 2 pieces of these two are formed. That is carbohydrate undergoes a oxidation, and the reagent phenylhydrazine becomes into reduction. So here already one hydrogen is there, and the second carbon will become now the ketone, that is an oxidation reaction. So the rest of the R1 will be intact like that. Okay. Now this is the first mole I am adding, second mole used for the oxidation. So I will use in fact the excess of the phenylhydrazine. So the third mole is consumed now to get this reaction here. So third mole of the phenylhydrazine is used to make hydrogen with this carbonyl group. So you will get a 2 double hydrogen of the glucose is formed. Dihydrogen is formed. So a question may be asked, this particular compound is called glucose giving, so therefore glucosazone. Now the questions related to the glucosazone is, for each glucose, to get the glucosazone, how many phenylhydrogens are used? One used for getting hydrogen, second used for the reduction, that is oxidation of the compound, it undergoes reduction to get the aniline, and this one. Third mole is consumed for the again hydrogen. This is one question. Another question is, if the second carbon actually is not having a carbonyl but it is oxidized, if that is so, why not the third carbon undergoes again oxidation and goes into the one more phenyl hydrogen? Means here comes one stable structure between the N and the NH, comes a hydrogen bonding. You can write like this beautifully. Either way you can write N with a double bond, N with a hydrogen phenyl. This is N NH phenyl. So this hydrogen bonding shows a beautiful 6-membered ring, and stabilization comes. Whenever stabilization comes, molecules will get reactivity will become decreased. Therefore, it will not undergo further oxidation and the further formation of the hydrogen formation. So, only two carbons, first carbon hydrogen, second carbon oxidized and again hydrogen. So, double hydrogen level it will stop. So, that was the reason explained why it is not giving. So, surprisingly, you take fructose. Fructose will contain the what symmetry? The first carbon non-chiral OH, second carbon is a non-chiral carbonyl. At third and fourth and fifth, let us say it will having the some symmetry, we don't know, having the R2. It is surprisingly what happens if here also 3 molecules of phenyl hydrazine is used, and what is expected is fructose should give the fructosazone, but first mole is used for this one, second mole is oxidized this one into the aldehyde and again gives this one. So, fructosazone also giving the glucosazone. It is identified fructosazone and glucosazone are same. So, what point we are proving here means the symmetry at the second and the third in the fructose, this is glucose, isn't it? In the fructose the symmetry at second carbon is ketone, second carbon, third one is OH, fourth one is OH, fifth one is OH. So, this particular part 3 chiral carbons in the glucose and the fructose is identical. Last one is anyhow non-chiral part. So, this part if it is same, this head if it is converted to hydrogen, this is osazone, and both will become same. So, therefore, this point entire exercise shows that the glucose and fructose will have the C2, C3, C4 symmetry is identical. At C2, at C3, at C4 the symmetry is identical, that is third OH right side, fourth OH right, third second, that is in third carbon, isn't it? This is third, fourth, fifth. This is 1, 2, third, fourth, fifth. So, third, fourth, fifth and third, fourth, fifth will have the same symmetry we are proving. So, this osazone formation is an important the step in deriving the body of the glucose and the fructose is same, except they are differing in the first carbon and the second carbon. Here in the glucose first carbon carbonyl, in the fructose second carbon carbonyl. So, literally speaking, the fructose should not give the tolerance reaction, but it undergoes a rearrangement known as Lowry rearrangement. There is one rearrangement shortly called Lowry, but it is called a D. van Eykenski Lowry rearrangement, in which the glucose when treated with base, it shows a tautomerization. Let us say this is all having the R1, this is the glucose. The glucose, the hydrogen, that is 2 electrons will come and this polarizes and the hydrogen jumps there. So, a enol is formed, this en with ol is formed. Already ol is there. So, therefore, I call this one as a endiol. 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 So, 2 ols are there attached to endiol. This is what in basic medium happens. Basic medium tautomerization will be more the influenced. This is what even fructose will give the same compound. Fructose will have a ketone at the second carbon, OH at a first carbon. So, this ketone, these 2 electrons will come here, the double bond goes to into this one. Let us have a R1, because the body of the glucose fructose is same. So, this compound also will give this one. So, there is an equilibrium between this endiol through the endiol. Glucose, if you take in basic medium, it turns up into the fructose. So, if you take fructose also, naturally it becomes into the glucose. There is one more compound. While coming this H back, you need not to get the same compound, but you may also get one more compound where the aldehyde will be at the first carbon only, but the OH can be this side. This is called same glucose body will be there, but the second carbon OH on the right side. This glucose and this particular compound is called mannose. Glucose and mannose are said to be a C2 epimers. C2 epimers. C2 epimers. We have a stereoisomers in which the isomers which are totally mirror images are called enantiomers. If part is mirror image, if part is non-mirror image, they are called diastereomers. Under that special class here, only one carbon at this second carbon, it is mirror image to this one. The rest of the third, fourth, fifth carbons are same. So such two relationship is called what? Epimers. Specifically epimers are said to be with number C2 epimer, C3 epimers and so on. Whereas alpha glucose and beta glucose, alpha and beta glucoses, they go on exchange into one into the other one without any this one, just solvent. If water is there, they go on exchange, isn't it? Such a type of isomers, you may call it as a anomers, which is a special category of the C1 epimers, interconvertible. When solvent is there, the alpha glucose becomes into beta glucose, they are called anomers. Alpha beta glucoses are called anomers, and glucose and mannose are called this one. So therefore, if I add fructose tolerance reagent, strictly speaking, tolerance reaction it should not give, but fructose becomes into this glucose and then responds. So therefore, fructose also giving the positive reaction with toluene and failing. Both are basic medium, ammonical silver nitrate and alkaline medium of the Rochelle salt and copper sulfate is nothing but the failing. So both are alkaline medium. In the alkaline medium, even if you take pure fructose also, it becomes into glucose, and the glucose has an aldehyde, therefore it is giving the silver mirror with the tolerance and the failing with the copper oxide formation, cupric oxide formation, red precipitate with the failing. That's why the glucose gives the positive as well as fructose also gives. Both are reducing sugars. Cellulose is a polysaccharide which on partial hydrolysis will get cellobiose. Cellobiose on further hydrolysis will give the nothing but the glucose. So how this the glucose molecules are linked to the another glucose means if you take beta D glucose, so the first OH will be linked to the another glucose here, and the fourth OH is linked to the another OH here. Second one will be OH down, third one is up, fourth one is linked, fifth one is CH2OH. Like this, one glucose at first carbon, another fourth carbon is linked to the another glucose. So therefore, through the first carbon it is linked to the further glucose through the fourth carbon. This is called C1-C4 linkage. C1-C4 linkage. And it is also said if only two molecules, if you take one glucose, let us write like this. So this is a OH, okay, OH, fourth one is down, fifth one is CH2OH. It's a dimer actually, cellobiose structure, second, third, fourth one, fifth one, CH2OH. Now this is one glucose unit, this is another glucose unit. When you this cellobiose, if it is added to water, what happens? At this the first carbon OH is linked to the fourth carbon, therefore it cannot open. But whereas at first carbon you have this anomeric carbon, the H can come back to this, it will become hydroxy and this will become aldehyde. So therefore a structure may become into this hydroxy function and may become into a carbonyl function. So therefore this particular opening makes you to get an aldehyde. Therefore when you add tolerance reagent, it is again giving a positive test. Though it is disaccharide, at one place you can open it. Here this the back one is not able to open, but the front one it can open into aldehyde, because when water is added it can go open into the open end cyclic. So open structure will have a aldehyde, therefore it is going to reduce. If both the ends are tied with that is C1 connect, this in this is C1-C4. If C1 is linked to the C1, in another case if the C1 is linked to the C1, none of them will open up into the aldehyde. In such a case, if you add tolerance reagent, no positive reaction, a negative reaction. This is called a non-reducible type of the sugar. But whereas in many cases they are reducible sugar. At least one will be open up. So even in the sucrose also, glucose, fructose will be there, and the glucose can open up into the system. So therefore it is giving a reduction reaction, that is oxidation with the tolerance reaction. So the cellobiose, for example, it is a disaccharide, but still it reduces the tolerance reagent, that is oxidizes, so oxidized into the acids, and tolerance reagent is reduced to the silver mirror. Therefore it is called a reducible the disaccharide. So some more examples we'll take from the carbohydrates to give the more clarity over the specifically enantiomers and the diastereomers. If a 3 carbon carbohydrate, if you take, there are 3 carbons are there. Only the middle carbon is having the optical activity. The top one and the bottom one is a non-chiral. So therefore you can club up the groups. So this is the Fisher model of the glyceraldehyde. Its mirror image will be there. So OH will be left side and the hydrogen will be the right side. The rest CHO, you need not to write double bond O and split up pattern, not necessary. So the first one, the OH is right side. So it's configurationally the OH is the important group right side, therefore you call it as a D-glyceraldehyde. You can also use IUPAC name as a 2,3-dihydroxypropanol, but say D, capital D refers to the important group is on the right side. That too, if so many chiral carbons are there, the capital D refers only the last chiral carbon, or the from the bottom side first chiral carbon. Okay. So the OH here it is left side, though you call it as a L-glyceraldehyde. It so happened in the carbohydrates, all the carbohydrates so happens, all capital D compounds are specially showing the dextro property. The D refers to the configuration, this small d refers to the optical activity, or you can show the plus glyceraldehyde. This is called a capital small L or a minus glyceraldehyde. The small d and the positive nature shows the optical activity, whereas the capital D refers to the OH. So these two are said to be a set of enantiomers. If I say compound A and the compound B, this A and B are said to be a enantiomers. As per the definition, enantiomers are totally non-superimposable and mirror images are said to be enantiomers. If 4 carbon series if you take, there will be 4 compounds and these 4 compounds, the aldehyde and the alcohol is common. At second and third, we have a 2 OH groups right side. The second isomer will have the 2 OHs on the left side. So this compound 1 and compound 2, let us say 1 and 2, is a set of the enantiomers because they are exactly the mirror images of each other. And the second compound, third compound, 1 OH right side, 1 OH left side. The top and bottom will be the same aldehyde and the alcohol. Now this OH is mirror image and the mirror image of the second one. So if I number these compounds 3 and 4, so 1 and 2 are called capital D erythrose and capital L erythrose. Erythrose is a common name we are using when 2 OHs on the same side, erythrose. If one this side, one that side, we are using triose, and this OH is happens to be a right side, I used D. So therefore this is also capital D triose. Its mirror image will be the L triose. As I said, in all carbohydrates, capital D happens to be a small d. So small d or plus erythrose is nothing but same one, and small L or the minus value showing the erythrose is nothing but same. This is a small d or the plus. In other compounds, this capital D compounds may show the LEVO property, but in carbohydrates, they are coinciding. Now, the interrelationship, if you see, 192 is called a set of enantiomers. 3 and 4 is also a set of enantiomers, same enantiomer set. But if 1 versus 3, if 1 and 3, 1 and 4, 2 and 3, 2 and 4 is called diastereomers. Diastereomers. Diastereomers are not enantiomers, they are stereoisomers, however, but not the enantiomers. Non-enantiomeric stereoisomers, you can call it as a diastereomers, but the diastereomers also can be viewed like this. For example, if 2 and 3 is a diastereomer, if you see this part is identical, whereas this part is a mirror image of this part. Okay, so second part is a mirror image, the lower part is a mirror image, but the upper part is ditto. That means if it is total compound is mirror image, I could have say enantiomer. If total is the same, I could have say homomer, that's nothing but the same molecule. So half the part, that is out of the 2 chiral centers or out of the 4 5 chiral centers, a certain number is ditto symmetry, a certain number is the opposite symmetry. So such type of the mixed type of the relationship is called diastereomers. Definition, you can define a part of the that is the stereoisomers which are not enantiomers, or stereoisomers which are non-superimposable, non-mirror images, you may call it as a diastereomers. But it so happens even geometric isomers like cis-2-butene, trans-2-butene also fits into this definition. Therefore, cis-2-butene, trans-2-butene also said to be a diastereomers. So, like this, in the 4 carbon series we have 2 erythroses and 2 threoses. In the 5 carbon series we will have a 3 chiral centers. So, therefore, 2 to the power of 3 means total 8 compounds, of which 4 will be the that is D series, that is erythro, that ribose and arabinose, lyxose and xylose, and 4 will be the L series. Now, here if somebody asks, write its a first compound is given, D threose is given, write its enantiomer, means it is not the one OH opposite, it is the total compound mirror image you have to write. Once a question was asked on the D glucose, write the D glucose that is the L glucose structure. D glucose was printed and asked L glucose structure. So, it is not the one the last carbon, but the total compound you have to write. All the OHs in the D glucose, third will be on the left side. So, you have to write the third will be on the right side. Like that, all the OHs opposite configuration if you write, it will get a enantiomer. Otherwise, it will become a diastereomer. So, like this here, D erythrose and 3 L threose are the total mirror image, it will be the enantiomer. Otherwise, it will be a diastereomer.